All right, today we're diving into a real chemical mystery, one that's hiding in plain sight right there on the periodic table. We're talking about unexpected behavior, hidden forces, and elements that, well, they just seem to break all the rules.
You know, we usually think of the periodic table as this perfectly organized map, right, with all these predictable rules. But then you get to this one particular neighborhood. We're talking about the D block, and the most fundamental rule of all, atomic size, just gets, well, weird. So what in the world is going on here?
Okay, so the rule we all learn in chemistry class is pretty simple. As you move from left to right across a period, atoms are supposed to get smaller. Makes sense. But check out the D block. Something totally different happens. Yeah, the shrinking starts, but then it just stops. The size pretty much flatlines. And that right there, that's our first big clue that there's some kind of hidden force at play.
So to figure this out, we've got to go inside the atom itself. It turns out there's this constant battle happening, a real push and pull. Let's unpack this first piece of the puzzle, shall we?
It really all comes down to this three-way tug-of-war. First up, you've got the pull. It's exactly what you'd think. As you add more protons to the nucleus, its positive charge gets stronger and it pulls the electrons in tighter, so the atom shrinks. Simple enough, right? But here's where it gets tricky. The second part is what we call poor shielding. See, the new electrons are being added to an inner D subshell. And these d-electrons, they are just terrible at shielding the outermost electrons from the nucleus's pull. It's kind of like trying to block a giant magnet with a piece of paper. It just doesn't work very well. And then finally, you have the push. As you keep cramming more and more electrons into that same D subshell, they start to get crowded. And since they all have negative charges, they start repelling each other, pushing back out against that nucleus's pull.
And this whole incredible balancing act? Well, it has a name, the D block contraction. This is exactly why the atomic size just flatlines for these elements. That inward pull from the nucleus and the outward push from the electrons, they almost perfectly cancel each other out. And it's all thanks to that really weak shielding from the d-electrons.
Oh, and by the way, this isn't just some weird thing for neutral atoms. This exact same push and pull dynamic applies when these elements form ions too. So the logic holds up across the board.
Okay, so puzzle solved for moving across the D block, right? But what happens when we go down the table? This is where the story takes a real plot twist. A new and even more powerful force enters the picture.
Now, again, the basic rule here is super simple. When you move down a group on the periodic table, you're adding a whole new shell of electrons. It's like adding another layer to an onion, right? The atom should get a lot bigger. So you totally expect an element in the 5D series to be way bigger than the one right above it in the 4D series, right? I mean, it seems obvious.
Well, take a look at this. The actual data tells a completely different story. We've got zirconium from the 4D series and hafnium sitting right below it in the 5D series, and their atomic radii are nearly identical. No, seriously, they are pretty much the same size. This just completely shatters our expectations. A whole new layer of electrons was added, but the atom didn't grow. How is that even possible?
Okay, the culprit has a name, and it's called the lanthanoid contraction. Here's what's happening. Right before you get to those 5D elements, the periodic table takes this little detour through the F block to fill up the 4F subshell, you know, the lanthanoids. And listen, if you thought D electrons were bad at shielding, F electrons are abysmal. They're just terrible at it. What this means is that the outermost electrons feel this incredibly powerful, almost unshielded pull from all the protons in the nucleus. And that pull is so intense that it completely cancels out the size increase you'd normally get from adding a whole new electron shell. It's wild.
And look, these atomic-level quirks, they aren't just fun facts for a chemistry test. They have really profound, real-world consequences for how these elements actually behave. This leads to a super fascinating effect.
So here's the bottom line. An atom's size pretty much dictates its chemistry. And because zirconium and hafnium are almost the exact same size, thanks to that lanthanoid contraction, their chemical properties are, well, they're astonishingly similar. They basically become chemical twins. You find them together in nature all the time, and they are notoriously difficult and super expensive to separate from each other.
This chart just tells the whole story perfectly. Look at the 3D series. You see that big drop in size as you go across? That's the normal trend we expect. Then you get to the 4D series. The D block contraction starts to kick in, and you can see the drop is much, much smaller. But then, by the time we get to the 5D series, that lanthanoid contraction is in full force, and it's so powerful that the size barely changes at all. The whole thing just about flatlines.
All right, so let's put all the final pieces of this puzzle together. What are the big takeaways here?
It really all boils down to two key forces. First, you've got the d-block contraction. That's where the poor shielding by d-electrons makes atoms basically stop shrinking as you move across the row. And second, there's the even more powerful lanthanoid contraction. This is where the absolutely terrible shielding by f-electrons makes the 5D elements almost the exact same size as the 4D elements right above them. And the ultimate result of all this, you get this strange and wonderful phenomenon of chemical twins.
It just goes to show you that even a map that seems as orderly and structured as the periodic table, there are these incredible hidden forces at play, bending and sometimes even breaking the rules. It kind of makes you wonder, what other invisible forces are out there, shaping the elements and the world all around us?